afternoon, everybody. It's time again for some pre-calculus. This is our second live stream class meeting of the semester, and it's really the first one in which we're going to meet the main players that are going to be on our stage, not just for the rest of our semester of pre-calculus, but also as you move out of this course and into the next course and begin learning calculus proper. What we're beginning to talk about today are also the objects of study from calculus as well. The topic we have today is functions. Functions take absolutely the center stage in pre-calculus and calculus, and they're really what make these subjects different from the algebra classes that you had prior to this. Because functions are the main tool that mathematical analysis uses to be able to model situations from the world around us, for example. Functions are really ways of describing how two quantities that maybe we can measure from the world. Maybe it's a physical science problem, maybe it's a social science problem, maybe it's an economics or a business problem. We have two things that we can measure, and they're related to each other in some way. And a function can be usually a function is what we use to describe the relationship between those two quantities. So if I'm a major in business marketing, for example, I might have a new product that I want to sell, and I go out and I do some test market research, and I find out that how many of these products that I can sell in one of my markets depends on the price that I want to charge for that product in the market. And as the price that I want to charge goes up, the number that I can sell at that price goes down, and vice versa. So there's a relationship between those two measured quantities. And we use a function to describe the nature of that relationship. And if we understand how two quantities are related, then, and this is the holy grail of calculus, we can predict how changes in one of them will affect changes in the other. Not just does one of them go up or the other one go down, but also at what rate. That's one of the main questions that animates our study of calculus next semester. So this is really the beginning of a very long story of mathematical analysis, thinking of functions as not just relationships between measured quantities, but also thinking of them as things in and of themselves, not just verbs that describe something that's happening or doing relating to quantities, but also as nouns, as objects themselves that we can study. And so what we're going to do today together is we're going to talk through sort of some introductory topics in the subject of functions. And every one of these topics that we talk about, I want us to be able to be conversant and to understand it in no less than 4 different ways. And I want to sort of talk really briefly through what these 4 different ways of understanding are. This is a frame that I like to use in just about any math class that I teach. Because I feel like it not only enhances our ability to communicate a mathematical idea, but also, hopefully for you, it helps you to understand these topics in the first place. Because the more different sort of modalities, the more different ways that we can look at a topic, the more likely that one of those is going to stick for you as a learner of mathematics. So one of the ways in which we're definitely going to have to talk about all of these ideas is algebraically. In other words, using formulas and algebra and all of those wonderful the techniques that we learn from our algebra classes themselves. We can understand what functions are and all these different function properties we're going to talk about today from the perspective of algebra. And this is probably the one where the actual meaning of the algebraic manipulations that you're doing is the most opaque, right? We're going to, in this frame of mind, we're going to do some calculations, some simplifications, maybe solve an equation here or there, but what's actually being done in those calculations from a conceptual, almost a moral standpoint, what that's telling us about functions, is usually not very well understood in the algebraic calculations themselves. It's much easier to understand today's ideas, I think, if we can visualize them. So we're going to be using graphs of functions to be a main tool for us to understand what's really going on, both in the definition of what functions are and also in some of the other properties we'll talk about today: domain, range, symmetries, and transformations. All of those, I think, are most readily understood by pictures that speak 1,000 words, right? So we'll definitely be looking at a graphical perspective on all of these function concepts as we go through the whole rest of the semester of pre-calculus and into the next semester in calculus as well. Graphs are a main tool, not just for our own understanding first and foremost, but also our communication of these ideas out to let's say, less mathematical audiences in the real world. Thirdly, but usually firstly, weirdly, is the numerical perspective. A lot of where functions get their usefulness in the kinds of mathematics that you'll do during and after this class is that we can use them to model relationships between measured quantities of data. And so the numerical perspective, just getting the data, understanding the data, is usually step one in a modeling process. But the numerical perspective can also shed a lot of light on what's happening in these concepts as well. So we'll be looking at how are these ideas reflected in a data table, a set of ordered pairs. And then the last one is also, I think, one of the most important ways of understanding a mathematical concept, and that is using words. After all, words are how we communicate with other human beings, for the most part, words and pictures, and not very often using algebraic formulas. Mathematicians communicate in that way sometimes, but most of the time, even mathematicians communicate with one another by using words. So we also want to be able to very carefully describe using words what's going on with each of these definitions and properties that we talk about today. So these 4 different lenses that we have to view mathematical ideas, I call these the rule of 4. And so for each one of our ideas today, we're going to try to take a look at it from each of those perspectives and try to do each one of those justice. From time to time, I might put a little timer on myself because I tend to get a little bit long-winded, especially in situations like a live stream where no one's listening and very few people are interacting with me in real time. Although you can, if you're my current student and you're watching this live as we speak, feel free to drop any questions or comments that you have about what we're doing into our Ask It channel in our class Slack discussion site, and I'll respond to them in real time. But from time to time, I might set a little timer on myself just to keep myself from devoting too much time to one perspective on one of these function ideas. I want to make sure that we have the opportunity to really get to them all over the course of our stream today. So let's get things started by talking about what is a function really. So what is the definition? Where do we begin in our study of functions and how they work? So weirdly, I actually kind of want to start by an equation. X to the third power plus y to the third power equals 3xy. And so I'm going to say, suppose that I go out into the world and I measure a quantity x and a quantity y. So I select a bunch of data points, I take them back to my lab, and I find out that the x and the y, the 2 quantities that I measured, happen to be related together by an equation like this. Right. So the first interesting thing about this, I think, is the idea that an equation can represent a relationship in the first place. So I kind of want to just take a moment to get us started just to think about that. In what way does an equation tell us about a relationship between 2 quantities, between an x and a y, for example? Well, one way to think about it is this. If you give me a value for one of these variables, if you give me an x, for example, then the job of this equation is to hopefully provide us with the corresponding y. The equation gives us a y. How does that work? Well, if you just come up to me on the street, as often happens to mathematicians, and you hand me a number that I'm supposed to use for the value of x, let's suppose that somebody comes along and gives me a 0 and tells me the value of x is this, the value of x is 0. Well, I can't just put a 0 in for x in this equation without then limiting the values that y can take in order for this equation to still be balanced, to satisfy on both sides of the equal sign. So if you give me x equals 0, then this equation responds by putting a 0 in place of every one of the x's that I see, and then the rest of the equation fills in around it. So I get something that looks like this, right? And when I simplify both sides of this equation, this 0 cubed becomes a 0. Multiplication by 0 over there gives me a 0 on the right-hand side of the equation. But what you notice is that now that the x variable is gone from this equation and only y remains, now the value of y is prescribed by this equation. I can solve it for y, right? And specifically here, if I solve y cubed equals 0 just by taking the cubed root on both sides, Or, as we talked about in our first live stream, that's the same thing as raising it to the 1/3 power on both sides. Then on the left-hand side, I'm going to get just plain y. And on the right-hand side, I get the cubed root of 0, which happens to be 0. So the point is that this equation describes a relationship, because if you give the equation a value for one of my quantities, the equation can be solved to determine the values, the corresponding values of the other. So if you give me x equals 0, then the equation is going to spit out for me y must be 0 as well. And so what that actually helps us to start doing is we can start building a numerical table of data based on those kinds of observations. So make sure we can see what we're doing here, right? If you give me an x, then the equation gives us a corresponding value for y. And in particular in this example, if you give me x equals 0, the equation gives me y equals 0 as well. Let me copy the equation down here in the corner just so we can still see it. X to the 3rd power plus y to the 3rd power equals 3xy. Well, things get a little bit more complicated, algebraically speaking, if I pick some different values for x. So for example, if I were to pick the value of -1 for x, then what's this equation going to do? This equation is going to replace the 0 that we had in here this last time around with a -1 instead. And it's just going to give me a different algebra problem that I'm going to somehow need to solve in order to determine what values y can take, right? Well, the issue here, -1 cubed is -1. 3 times -1 times y is going to give me -3y. But I end up with this equation that actually turns out to be quite difficult to solve. -1 plus y to the 3rd power equals -3y. And the best that I could do with this equation, really, I suppose, is add the 3y to both sides. But I end up with this polynomial equation that has degree 3. I have a y cubed over here. And if you're interested in how mathematicians have solved equations like these in the past, I have a whole YouTube playlist of hundreds of hours full of second semester abstract algebra that if you're a math major, you might be interested in looking at. In particular, a seminar called the Cubic Workout, which is a 1-hour-long seminar talk, which is about solving equations like this one. But for our purposes in a pre-calculus class where we're not all math majors, we're just going to sort of throw our pencils down at this equation and say, it's probably best if we thought about this in a different way. Maybe we use some technology to try to solve this equation. I'm going to try to pull up a computer algebra system here and see if we have any luck in solving this equation. I'm going to do a little off-screen typing for a moment here. I hope you'll forgive me. Y to the 3rd power plus 3y minus 1 equals 0. Let's see if this thing can solve it. Whoops. So this is the problem with typing on the fly. I know you can't see it, but I'm running into some errors over here. All right, I'm just going to try one more thing here and see if we can do it. No, not having any luck there. Okay. So the point is, this is not an easy problem in general to solve an equation that looks like this. So what's our next best tool for trying to figure out how to deal with difficult problems? How about seeing if we can come up with a graphical picture? Because if we can solve these equations, anytime I provide an x, I can solve the equation to give me a y. What it's going to do is it's going to give me a list of a whole bunch of different ordered pairs that we can get. And all the different ordered pairs are going to give me different points on the xy coordinate system. So let's take a moment here and pull up a graph. So this graph is coming out of Desmos. And if I pull it up on my screen, there it is. Whoops. Let me move it over so that we can see everything at once. I'm going to cover up this pane here for a second. Here we go. So we know, for example, based on the computation we've already done, that 0, 0, the point right here in the middle of the Cartesian coordinate system, is one of the points that is a part of this relationship. But if x equals -1, we couldn't figure out what the y-coordinate was. So rather than get bogged down in this, let's just use some technology to show us the complete set of points that satisfy x to the 3rd plus y to the 3rd is equal to 3xy. If I have Desmos graph that for me, what I get is this funny looking little loop. And this little loop has a name, just for the sake of math history. It's called the Folium of Descartes. Folium. And folium is sort of a Latin word. A Latin root means something like leaf. So it's supposed to have kind of a leaf-like shape. Anyway, it's the Folium of Descartes. And so all of the points that lie along this red curve here are going to satisfy the equation x to the third plus y to the third is equal to 3xy. So we came all of this way because we wanted to talk about what it means to be a function. Okay, so what's going to make this example qualitatively different from other kinds of examples that we're going to look at as the live stream today proceeds? Can this relationship between this x and this y be thought of as a function relationship, or are we completely out of luck on that front? So now is when I'm going to, first of all, put my Desmos graph back up on the screen here, just so that we can see. This is the graphical perspective on this equation now. X to the third plus y to the third equals 3xy. Graph looks like this red loopy thing. So what will it mean for this thing to be a function? Let's put the definition down on the board, and I'm going to give myself the 4 minutes for talking about this definition, because I think it's important that we're able to get to as much as we can today. So when I think about the definition of function, I'm going to think about something that I'm going to write down sort of verbally. I'm going to verbally define here what the definition of a function is. So what does a function mean from a verbal point of view? From a verbal perspective, a function is a relationship between two quantities. And we'll say y is a function of x. We'll say that exactly when, so this is my definition, if any x value that you provide for me, so any x that's chosen, let's say, any x which is chosen from a set of choices that we're going to talk more about during today's live stream. But that set of choices is called the domain of the function. And y is a function of x. If any x that we select from the domain of my function is related by whatever relationship that this function is describing, it's related to one and only one value of y. Okay. So y is a function of x means if you give me an x value, then this relationship has to supply only one y value for that x. Very often I think of a function as like a mechanism, almost like an input-output machine. And in the input-output machine picture, I've got a function, and this machine that I'm thinking of as a function has a little input hopper on the top here, and we put little x's, values of x go into the input of this machine, and out the other end of the machine is an output chute, and out the end of this output chute come values for y, my outputs. And this machine is a function because if I put in a single value for x as an input, every input that I put in is going to spit out a unique output. I can't have, maybe another way to think about this is what is something that's not a function going to do? Each input cannot have more than one possible output. It's another perspective. It's sort of the flip side of the coin. Cannot have more than one output. Each input cannot have more than one output. If I put, let's say I put the number 2 into my function, and the function machine spits out the number 6 as output. That means that every time I put a 2 into my function, I'm going to get a 6 out the end. There's no way for me to put in a 2 and get two different values, like 6 and I don't know, 11 or something, the output of this function. Every input has a uniquely defined output. That is what it means for a relationship to be a function. And when we use the verbal expression y is a function of x, it's this x, this thing that comes after the of, that we think of as the inputs, and the y's are what we think of as the outputs. So in our example that we just did a minute ago, when I chose a 0 for x, my equation ended up spitting out only one value, namely 0 again, for the value of y. It was not possible for there to be more than one y's for a given x. But does that necessarily mean that this relationship defines a function? And the key to that is right behind my head here. It's the word any. So if it's possible at all for me to get two different values of y for the same value of x, then we do not have a function. So my 4 minutes in this pane are up. Let's go to the graphical perspective next. So in our graphical perspective, we know that a graph can describe the locus of all points in the Cartesian coordinate plane that satisfy, whose x and y coordinates satisfy that given equation. And our graph looked like this, right? So my question now is, based on our understanding of function, let's slide this over here, based on our understanding of the definition of a function, how can I tell whether a graph describes for me a functional relationship or not? Let me start another 4-minute timer. So a graph of an equation, a graph depicts, oops, let me get some real typing here. A graph depicts y as a function of x if, and here I'm just going to repeat again the definition of function that we just finished talking about. If, let's say it the first way, if any x is related to only one y. And in other words, let's go back to that negative framing that we had a moment ago. The graph, the graph does not depict a y as a function of x if some value of x is related to multiple values of y. Right? So this is what mathematicians call the definition, and then the converse, not the converse, the negation of this definition. This is what it means to be the graph of a function. This is what it means to not be the graph of a function. So is it possible for one x value to produce multiple y values? Well, the way that we have to study that is we can draw on my graph here. We're using graphical reasoning, so let's just draw on this graph a graph of the vertical line x equals a. I think I have to force Desmos into doing things a little bit weirdly here. Okay. So here is a vertical line being drawn on my graph. It's a vertical line because what we've done here is we've specified a single value of x. In this case, we've chosen x equals 1, right? And if I choose different values for x, I just get different vertical lines. So for example, here's x equals -1. X equals -1, by the way, happens to be the value of x that we were trying to study right here, right? If you give me x equals -1, then if I can somehow miraculously solve this equation, then that equation will provide for me one or more values, or maybe none, for y. Well, looking at this graph, we now know how many values of y correspond to this values of x, because those values are just given by the intersection point of this vertical line with this graph. And according to this graph that we're looking at right here, it looks like the value of y, and there's only one of them, that corresponds to x equals -1, is about y equals 0.33. So given that, I'm going to put that approximation, just drop it into my data table that we had down here at the bottom. Not minus, 0.33. That's an approximate value for y when the value for x is -1. And so far, it doesn't look like there's a violation of whether or not this graph defines a function, because each single x value provided for me only a single y value. So far, we're seeming like we're satisfying this definition. But if we look a little closer, we say, well, what about an x value like x equals positive 1? What happens in this example? Well, when x is equal to positive 1, it turns out that there are no less than 1, 2, 3 different places where that vertical line meets this locus of points. And so for the same value of x equals 1, there are 3 different values for y, 1.53, 0.38, and minus 1.82. And so if I listed all of those in my data table, all of them would be related to the same x value. Minus 1.82, 0.83, 1.35, right? And I'm realizing I'm drawing off the screen here. So the tell, right, is that I have the same x value for 3 different y values. And that goes straight to the heart of not being a function. So we're now talking about numerical, so my timer has started over secretly. If the same x value has more than 1 different y values, then we have not depicted y as a function of x. And sliding back to our graph for just a brief moment, what we notice is that this vertical line at x equals 1 is intersecting this graph more than 1 time. And so what we're getting here is the following picture. And let's go back to seeing everything here for just a moment. So how are we going to know from a graph whether or not y is being depicted as a function of x? Well, what we get, what we've just sort of argued for, according to the definition of function, is something that students of pre-calculus will remember as the vertical line test. And the vertical line test says that y is a function of x on my graph only if every vertical line does not intersect that graph more than once. So again, I think it's easier to think about when and why this thing turns out to be false rather than true. So vertical line test says that my graph is not a function, or I'll say y is not a function of x, if some vertical line intersects the graph more than once. Intersects the graph more than once. And so in our example here, this green vertical line, and in fact a bunch of different green vertical lines, all of them drawn from here back over to here, all of those intersect my graph more than once. This one right here intersects the graph, it looks like twice, and then this one here intersects it 3 times. The vertical lines over here and over here intersect the graph only once. But as long as there is some vertical line that intersects the graph more than once, we can immediately stop and say y is not depicted as a function of x in this example. So that's what we call the vertical line test. It's the graphical tell for how we know when we have a function or when we don't. And the numerical tell that goes along with that is what we're seeing in this data table, right? This violation, having the same value of x being related to different values of y, same x, different y's, that again is a giveaway that we do not have y as a function of x. Y is not a function of x. Okay. So, these are sort of the various different ways of understanding how to, I would say, how to rule out a algebraic relationship being a function. If we can graph it and find out that it fails the vertical line test because there's some vertical line, like this one or that one or this one, that intersects the graph in multiple points. Or if we can draw out a table of data in which the same x value is being related to several different y values, then we know that y is definitely not a function of x in this example. So let's go forward and try and use these perspectives one more time with a different equation to see if we can repeat this process and figure out whether if we change the equation just a little bit, is this new thing going to be depicting y as a function of x? Sorry, I'm having an iPad freak out here for a second. So I'm going to change the equation into x squared y equals 1 minus y. Okay. And again, the question of whether y is a function of x is really the question, can a given x have multiple y's? Can a given x have multiple y's? More than one, in other words, two or more y's. And if that answer is yes, then y is not a function of x. And if the answer is no, then y is a function of x. Okay, so we now know what we have to investigate to answer this question. Let's investigate it this time in a slightly different way. Let's try and investigate this from an algebraic perspective. How could we use this formula to tell me whether a given x can have multiple y's? So to figure out whether an equation relating x and y describes y as a function of x, what we'll do is ask the question, can we solve this equation for y? And if we can, is there only one solution? Or maybe another way to say it is, could there be multiple solutions? Could there be multiple solutions? After all, we know from algebra that there are some equations that do have more than one solution. Quadratic equations generically have more than one solution. They can have up to two, right? So anytime we solve an equation, it's a valid question to ask how many solutions can this equation have? And so if there can be multiple solutions to this equation when I solve it for y, then a given x can have multiple y's, and so y is not a function of x. So we can put our algebra hats on, and we can solve this equation, x squared y equals 1 minus y, try and get the y by itself. This is probably not most algebra students' idea of a good time. But this particular problem is pretty tractable. So what I'll do here is I'm going to try to get all my y's on one side so that I can isolate them. I'm going to do that by just adding y to both sides, so that instead of having a y on the left and the right, I'll have it only on the left. So I'll do that addition. That's going to give me x squared y plus y. Oops, x squared y plus y equals 1. Now all my y's are on one side. Next I'm going to factor out the y because it exists in two different terms, and I'm trying to get it isolated so that I can get it by itself. I'll factor out that y. And when I do that, the cofactor becomes x squared from the first term and 1 from the second term. So there's what my equation looks like now. X squared plus 1, the quantity times y, is equal to 1. And then I'm just going to divide both sides by x squared plus 1. And what I get is this equation. Y equals 1 over x squared plus 1. All right, let's put that in a box and figure out what that means. Now that we've solved for y, we ask the question, can there be multiple solutions? If you give me an x, do I necessarily get a single value for y? And there, really the question is there any way to evaluate the expression that's on the right-hand side other than just following the order of operations, squaring x, adding 1, taking the reciprocal? And in this case, there is not. Could there be multiple solutions? There cannot. There's always only one way to make 1 over x squared plus 1 for a given value of x that you provide for me. Right? And so here, based on this observation here, this right-hand side is what we call a single-valued expression. And so is y a function of x? The answer here is yes, based on the algebraic calculation that we just did. Y is a function of x because any given value of x cannot give us multiple values for y. As soon as you tell me what x is, this expression defines a single value for y. Every input gives me a single output. And there's an algebraic perspective on it as well. Let's go ahead and take the numerical perspective. And I'm going to do the numerical perspective next, just because I think well, I'm going to use this as a way to introduce some more notation for us, because we haven't completely exhausted our algebraic understanding of how functions work. But in the numerical perspective, remember what we're doing is we're selecting some values for x, selecting some inputs, and then using the equation, which we could use this one, but now that we have this one turns out to be a little bit nicer to use at the end of the day. So we're going to use that equation, 1 over x squared plus 1. That expression, we don't need to do any algebra to discover the value for y. All we have to do is put in an x and simplify. So we're not doing any algebra, we're just simplifying an expression. And so because of this, we'll often give this expression a name. We'll call it f of x. So f now is the name of my function f. And it's being applied to an input value x. So you give the function f a value for x, and the value that it spits out is called f of x, and in this example it's defined to be 1 over x squared plus 1. So often we think of values of f of x as being kind of synonymous with y values on a graph. That's actually the definition of the graph of a function in the first place. The graph of a function is the set of all points whose y-coordinate is equal to the evaluation of the function on its corresponding x-coordinate. Y is equal to f of x. So anytime we're doing sort of typical Cartesian coordinate graphs, you can think of y and you can think of f of x as being synonymous. So when it comes to doing this graph, that's how we're going to get a graph of this function. But so now we have a deterministic way of, if you give me some values of x, let's say -4, -1, 0, 2, 5 or something. So we pick some values for x. And the equation, the expression 1 over x squared plus 1, is going to give us some y values. So let's use technology to actually do those evaluations, because I'm feeling like I don't want to do all the fraction arithmetic right now. And I'm also going to have Desmos plot those ordered pairs that we get out of this process. So if I pick for my first value of x equals -4. Then when x is equal to -4, the value that we get for y is this decimal right up here. I'm going to try to zoom in on it for you here for a second. 0.0588. If x is equal to -4, then 1 over x squared plus 1 is equal to this funny looking decimal. We could have written it as a fraction if we wanted to, but Desmos here is choosing to just use a decimal representation. But notably, there's only one value of y possible for any given value that I supply for x. So when I supply a -1 for x, I get, again, one and only one value. In this case, it's 0.5. When x is equal to 0, y is equal to 1. When x is equal to 2, y is equal to 0.2. And when x is equal to 5, y, 1 over x squared plus 1, is equal to this other funny decimal that we have over here. And now notice what's happening. As we generate those ordered pairs, each one of those ordered pairs becomes a point on the graph of this function. And so what's emerging here is a picture of what the graph of this function might look like based on just the first 5 of these ordered pair data points. And what's great about technology, graphing calculators or free graphing apps like Desmos that we're using, is that we can ask it to finish the picture. So to do that, I'm just going to write in here in an expression box, f of x equals 1 over x squared plus 1. And now that I've written that in here, it's showing me an entire curve full of points that happens to include the 5 points from my data table, but which also includes all of the points in between the data points that we started with. And that picture is a picture of what we call the graph of this function. So getting some data points, as we did here, is a good way to start the analysis of a function. But from those few data points, the hope is that the picture of the entire graph emerges. And we can use that picture of the entire graph to then answer the really good questions about this, such as, for example, is y a function of x? And to answer that question again, we go back to the vertical line test. Is it possible for any vertical line that we draw to intersect this graph more than once? And in this example, that answer is no. Any vertical line that I draw in this graph is going to intersect that red curve, the graph of my equation, the graph of my function, exactly once. There's no way for it to intersect more than once. And so that's how we can tell from this graph that y is being depicted as a function of x. So that is sort of a full set of perspectives on how to understand when something is a function, when y is a function of x. Y is a function of x exactly when it's not possible for a given value of x to have multiple values for y. If it is possible for a given x to have multiple y's, then y it cannot be said to be a function of x. Maybe the last thing I want to do here is just to do one more quick example to, again, illustrate from the algebraic perspective what would happen if y were not a function of x. So let's just take that perspective one more time here. So let's change the game. I want to change my equation a little bit. And my new equation is going to be x squared plus y to the fourth is equal to, let's say, 18. No, 20. All right, so I just made up a new equation relating x and y together. And so let's take the algebraic perspective, which is if I try to solve this equation for y, how many solutions am I able to get for x? Is it ever possible for me to have more than one solution? And then we'll also look at this from a numerical perspective as well. Let me erase my chicken scratches down here. Okay, so let's start by taking the algebraic perspective. Because again, I think for students, this is the one that's the most opaque. It's the hardest one to really understand what's happening. So in that algebraic perspective, let's try to solve this equation. X squared plus y to the fourth equals 20. Let's try to solve it for y. Try to get the y by itself. Well, getting the y by itself is first going to require me to get all the y's on one side and everything that doesn't have a y on the other side of this equation. To do that, I'm going to subtract x squared from the left side as well as from the right side. That's going to give me y to the fourth equals 20 minus x squared. And now to get this y by itself, what I need to do is take the fourth root on both sides. In other words, I need to raise both sides to the 1/4 power. And I end up getting an expression on the right-hand side, 20 minus x squared to the quantity 1/4, which looks as though it has a single value for a given value of x, because it does. The problem in the algebra that we're doing here, though, is that I'm taking a root that has an even index. The denominator of my rational exponent here is 4. Even index root. And anytime we're taking an even index root, there is a sign ambiguity inherent to that root. And what that means is that y to the fourth raised to the power 1/4 does not simply cancel this 4 times this 1/4, but it does so in absolute value. So when there's an even index root, we can't ignore the fact that if I take a negative number and I raise it to an even power, I get the same answer as if I raise its absolute value to that even power. And for that reason, when I take the fourth root, we end up splitting the values of y that we can get here into a negative version and a positive version. And when that absolute value sign goes away, and we get y equals, on the right-hand side of the equation, we get a sign that we don't use enough in mathematics, but it's a cool one, the plus or minus sign. So, real quick recap of what just happened. When we take the even root of an even power, we introduce a sign ambiguity, because if y is negative or y is positive, we're going to lose that distinction here when I raise those numbers to the 4th power. And so, when I take this even root, we get the absolute value of y. We don't just cancel the root with the power. And when I solve for y, when I finish getting that y by itself, the absolute value goes away and becomes a plus or minus on the other side of the equation. And so that plus or minus is actually the key to our answer to this problem. Is it possible for there to be multiple solutions for y for a given x? And in this case, because of that plus or minus, and only because of that plus or minus, the answer is yes. There are values of x that I can supply that give me multiple different values for y. For example, if I take x equals 0 in my data table here, then 20 minus 0 squared is going to be 20. I'm going to get the fourth root of 20, but I'm going to get both the positive fourth root of 20 and the negative fourth root of 20. Fourth root of 20 and minus the fourth root of 20. Same value of x, two different values of y. And that is the no-no, right? That is what it looks like when y is not a function of x. Now let's go to the graph. Again, the wonderful thing about technology is that it's going to allow us to just sketch this graph directly right in there. Let's see what the graph looks like. Just open our Desmos grapher and type in x to the second power plus y to the fourth power is equal to 20. And lo and behold, this graph, this red set of points, does not pass the vertical line test. As I sweep this vertical line through, almost every vertical line that intersects this graph at all intersects it more than once. It intersects it twice, once up here on the top and once down here on the bottom. Right? So for example, if I pick x equals 2, then the vertical line that we call x equals 2 intersects at y equals 2, but it also intersects at y equals negative 2. Okay. And so again, same value for x, two different values for y. And that's the giveaway that y is not a function of x in this relationship. So that's our introduction, and that is the part of today's live stream that I wanted to take the most time on, just because I feel like this is where the concept is really the most important. That what a function is a particular kind of relationship between two quantities, one in which the input quantity, sometimes called the independent variable, that we often label x, any single value of x is going to determine uniquely a single value of y. In a function relationship, if y is a function of x, it's not possible for one x value over here to produce multiple y values over here. One x value relates to only one y value when y is a function of x. So what comes next? Now that we understand what a function is, we want to go through sort of the main really important property of a function. The first thing that we really are going to want to know about a function, and that is going to be the two properties that are called domain and range. What is the domain of a function? What is the range of a function? And how can we understand those questions from, again, all four of our different rule of four lenses? So let's go back to the whiteboard for a minute. And let's look at the following problem. I'm going to try to wake up my iPad here. Looks like we're going to have to relaunch real quickly here, so just please bear with me for a second. Just going to have to reset my iPad. Come back in here. Come back in here. And make an adjustment. All right, here we go. Get back to where we're going. Perfect. So here is a new function. And notice what I've done here is I've given this function the functional notation. So f is the name of my function. X is the input to my function. And what my function machine does to x is it takes its fourth power, it subtracts that power from 16, it takes the square root, it takes the reciprocal, and then it flips the sign. So there's a lot of different gears inside the machine that we're calling the function f. So it does a lot of different stuff. So how am I going to find the domain? How am I going to find the range of this function? First of all, what do those two words even mean? That's the verbal perspective. The domain of a function is, first of all, a set. So you'll maybe remember sets from your algebra classes, when we say set, we're talking about a collection of objects, not a single object, although we can think of sets as a single thing, but sets are characterized by having constituent elements in them. So sets are whole buckets full of elements, and in this case, the elements of numbers. And it's the set of all numbers that my function can accept as input. So that's the long-winded sort of verbal description. It's everything that I can fit into the top input hopper of my function machine, if you like. So just to get us sort of started thinking about what the algebraic perspective of this function might be, let's draw out f as though it's, again, one of my big machines here. And in the top of this machine, we put values of x as input. And following the order of operations, what happens to those x's is that they get raised to the fourth power, and they become x to the fourth. And then at the next step, we end up subtracting that quantity from 16. So 16 minus blank. I'm going to kind of write it like that. And that's going to turn it into 16 minus x to the fourth. Looks like I might need a longer machine over here, because then the next thing that happens is that we take the square root. So this little step is the square rooting step. And then we become the square root of 16 minus x to the fourth. And then at our last step, we'll call this our last step, we take minus 1 over blank. Think of that as the opposite reciprocal step in the process. And it's at that step that we are finally done with our function. And out the bottom of this function drops the value of f of x, which is minus 1 over the square root of 16 minus x to the fourth. So that's my function machine. And the domain of my function is everything which is possible to put into this function up on the top, right? So as to get an output down here at the bottom. And if we want a shortcut way to understand domain, this is all possible x, if we think of x's as representing the inputs to my function. Okay. Alrighty. So that's what domain means from a verbal perspective. Let's take the graphical perspective for a minute. If we're looking at a graph of a function, how do we understand what the domain of that function actually is? So let's bring up our grapher one more time. And I'm just going to ask Desmos to please kindly graph f of x equals minus 1 over the square root of 16 minus x to the power 4. And here's the graph that Desmos produces for this particular function. Kind of try and let me zoom in on this a little bit so it's easier for us to see what's going on. So here's the graph of this function. The first thing that we might notice is we get some validation, at least, for the notion that this really is a y as a function of x. Any vertical line that I draw here is only going to intersect this graph at most one time. Some vertical lines look like they don't intersect this graph at all, but those vertical lines that do only intersect the graph in one point. So this graph passes the vertical line test, and that at least gives me the reassurance that we are indeed talking about y being a function of x in this example. But what is the domain? The domain is the set of all numbers that f can accept as input. And when we think about a graph, the x's are the inputs, input values. So if we want, we could even sort of label the x-axis input values and label the y-axis output values from my function, right? And with that perspective, if the question is, what does the set of all possible inputs look like? Well, here's how I like to think about that. I'm going to have Desmos make me a cool graph here. And we're just going to do that. Okay. And then this is going to go from there to there. All right. So here's the idea. To find the domain, we're looking for the set of all x values that we can possibly stuff into this machine, all the x's that have y's. So an example of an x value that would not be a part of the set which is the domain of my function is x equals -3. Right? When x is equal to -3, there is no point on my graph that has an x-coordinate of -3. Right? The vertical line at x equals -3 does not intersect my graph at all, anywhere. Right? So x equals -3 does not belong to the domain of my function. Meanwhile, x equals 1 does belong to the domain of my function, because there is a point on my graph whose x-coordinate is 1. Its y-coordinate is -0.258 or whatever. It doesn't matter what its y-coordinate is. It has a y-coordinate. And so the x value 1 is part of the domain, where the x value -3 was not a part of the domain. So how from a graph do I figure out what the domain of a function is? My favorite way of understanding this is we're just going to take that graph and we're just going to smush the graph onto the x-axis and figure out how much of the x-axis is being covered up. If I do that, then what do we get? Let's smush the graph down to the x-axis and see what happens. Smush, smush, smush. Oh, whoops. Hold on. Looks like I need to change my step size here. All right. Let's smush the graph down to the x-axis. Uh-oh. So when I smush this purple graph down onto the x-axis, it's not going to cover up the whole x-axis. In fact, the only part of the x-axis that gets covered up is the part between x equals -2 and x equals 2. And that's material to our conclusion here. So in the graphical perspective, I can figure out what the domain of this function is by smushing the graph onto the x-axis. I'm going to write this down in the numerical portion here. So the x's that have y's, the inputs which have outputs, are all of those between -2 and +2. -2 and +2. All right, so that's a pretty good answer for this question. We haven't really gotten to the algebraic part of it yet, but having a graph, again, the picture is speaking 1,000 words. Having a graph is great. It just means take the graph, smush it onto the x-axis, figure out how much of that x-axis you end up covering up. In our case, it's just the part from -2 to 2. But mathematicians would say this is kind of an incomplete answer, because when you say between, you're not telling the reader whether or not these numbers themselves, 2 and -2, actually belong to this set, or whether they should be excluded from this set. And for that reason, we tend to use a notation when speaking about subsets of the real number line that conveys that information. And that notation is called interval notation. And of course, the way that interval notation works is when we describe an interval of the real line, we have to specify the leftmost extent of that set and the rightmost extent of that set, with the understanding that everything between that leftmost and rightmost point is included in my set. And so in my interval notation, I do that by writing a comma in between -2 and 2. Right. So everything between -2 and 2 is included in my set. It's included in my domain. It's included in my answer to this question. But what about -2 itself? Is -2 in the domain or not? What about 2? And the answers to those questions help us to complete the interval notation. Let's go test it. Is 2 in the domain of my function? Well, according to the definition says, can we accept 2 as an input to this function? Can 2 be a value for x? What happens? Well, we just try to evaluate f of 2 and see what transpires. Right, this is the algebraic viewpoint on how this all works. So for f of 2, I've got -1 over the square root of 16 minus 2, that's my value for x now, raised to the 4th power. So what's going to happen? Well, according to the order of operations, the first thing that happens is 2 gets raised to the 4th power, and it becomes 2 to the 4th. But 2 to the 4th is 16. And then I subtract 16 minus 16 underneath that radical. 16 minus 16 is going to give me 0. So I have -1 over the square root of 0. then I take the square root of 0. And the square root of 0 is 0. Then I try to take the opposite reciprocal of 0. And the problem with that is that we cannot take the reciprocal of 0. Dividing by 0 is undefined. Right? Division by 0. 0 in a denominator means undefined. That's something we remember from the first topic of the semester where you're working with rational functions, rational expressions. Anytime the denominator of a rational expression becomes 0, that expression is undefined. We cannot divide by 0. And so the answer to the question, can 2 be a value for x, is no. Because when 2 is a value for x, there is no output from this machine. Because the machine breaks right here at this very last step where we try to take the opposite reciprocal, right? My 2 was able to be raised to the 4th power, subtracted from 16, and square rooted. But it was not able to then be taken the reciprocal of. Right? So 2 is not in the domain. And for that reason, the interval notation uses a round parenthesis right here. That round parenthesis means not included. This endpoint is not a part of my set. Oh, and I guess it was positive 2 that I tested up here, but both positive 2 and negative 2 after the very first step in this machine are going to give us the same, 16. And so whatever happened with negative 2 is also going to be the same thing that happened with 2 in this example. And so round parentheses on both sides of my interval notation. And so that interval, -2, 2, with round parentheses on both sides to indicate that neither of those endpoints is a part of my answer, that is the domain. It's the set of all allowable x values that give me y values for this function. So that's for the that is for the domain of a function. If one of these endpoints did happen to be able to be included in my perspective, I would have used a square bracket instead of a round parenthesis for is included. That just didn't happen in this case. So it's worth just doing a quick review of how interval notation works, just to make sure that your head is on right for how to actually use that way of communicating. So if that's how domain works, what's the flip side of that coin? Okay, what's the range? Well, as you might expect, range is also a set. So the answer to a range question is never a number, but it's a collection of numbers. It's the set of all numbers that f can produce as output, rather than accept as input. And so, where the domain concerns possibilities for x, the range concerns possibilities, realized possibilities for y. So again, we have sort of this mental shortcut. All attainable or attained values of y. All the y's that this function can produce as output. So what is that going to look like from a graph? Let's take the graphical perspective one more time. I'm going to have my grapher here give us a neat visualization of this in just a moment. And then my t values are going to be all the t's in my domain. All right. So my question now, right, to find the range of my function is what are all of the different y's that can be realized as values of this function? So now, where the domain involved us squishing our function's graph onto the x-axis to find out how much of the input values are possible, for the range, we're going to squish our function onto the y-axis instead. And all of the y's that are values that are realized by this function will be shown as a subset of the y-axis. So let's squish my graph onto the y-axis. And when I do that, I'm only covering up a portion of the y-axis. I'm covering up the portion that looks like it goes all the way down to negative infinity, right? I could scroll down through this graph, and sure enough, it never stops going, right? But it only goes up as far as this point right here. Whatever that point is, we'll figure out what it is in just a second. But what it looks like here is that the portion of the y-axis that's covered has no lower limit. So let's go back to our sketch here. If I want to know the y's that get realized as output values of this function, you can think of it also as the y's that have x's. They have no lower limit whatsoever. And so in my interval notation, I'm going to use the symbol negative infinity to represent that the range, the y values for my graph, they never end. However far down that I want to try to scroll, I'm never going to run out of graph. Okay. So minus infinity is the lower limit. And anytime we have an infinity in our interval, since infinity is not a number, we can never include it. So we'll always use a round parenthesis anytime an infinity is used in your interval notation. So there's no lower limit to the range on y's. But there does appear to be an upper limit. Let's zoom in. The more that I zoom in on this, I think hopefully the clearer picture that starts to emerge here, that the value of y, which is the largest value possible, is that value that's taken when x is equal to 0. And, just going to zoom in on this for a second, that value that this function takes when x is equal to 0 is negative 0.25. We could have known that just by plugging x equals 0 into the expression that defines my function, right? If x is equal to 0, which is a part of the domain of this function, then the value for y is negative 1/4. Now, it's not always true that the range of a function is defined by some value when x is equal to 0. It just so happened in this example that it did. Okay. So the question of what is the range of a function is actually very challenging to determine algebraically. It's, in fact, generically not possible to determine the range of a function algebraically. We really need some more sophisticated techniques. Let me finish talking about this example before we get a little bit of a preview of what those techniques might be. Because we haven't quite finished our interval notation. Right? We know that that portion of the y-axis, which is covered by my graph, goes up as far as negative 1/4, right here. And it goes down with no limit at all. It goes down to negative infinity. But is negative 1/4 actually an element in my set? Is it actually a value of y that gets attained by my graph? And the answer here is yes, it is. I'll put a square bracket here because negative 1/4 is in the range. And it's in the range exactly because it is a value of f of x, right? It's in particular the value of f of x when the value of x is equal to 0. So 1/4 is in the range, and so I'll use a square bracket to show that. But actually finding a range of a function using algebra is challenging. Finding a domain, on the other hand, so I want to return to this question one more time before we move on. How do we find the domain of a function using algebra? And the way that I like to do this is to do what I've done over here on the left and sketch out the various sort of pieces, the parts, the cogs that make up this machine algebraically. And the best way to figure out what the domain is to figure out which of these pieces of my machine, figure out which gear can break. In other words, you look at the formula and you ask yourself, what could possibly go wrong if I try to evaluate this function for a specific value of x? And the only part of my, well, not the only part, there's actually 2 gears in this machine where something can go wrong. The first step, there's no problem. Every single real number can be raised to the 4th power. And so raising something to the 4th power works for all real numbers. For all numbers. Sort of write it like that, right? So the first step, x to the 4th power, no problem. Same thing with the second step. If I want to subtract a real number from 16, there is no restriction on what numbers can be subtracted from 16, right? So both of my first 2 steps in evaluating this expression have no restriction on their domain. The third step, on the other hand, is the square root step. And not every real number has a real square root. And so here we get a restriction that whatever we have on this step cannot be negative. And so we have a restriction on our domain. By the time the value of our expression gets to this step, 16 minus x to the fourth, that value of that expression needs to be greater than or equal to 0 in order for the machine to keep working. Because if 16 minus x to the fourth is negative, then this square root step is going to break the machine, because we don't have a real square root for a negative real number. This is why, coming back to our graph for a second, if I pick the x value, x equals negative 3, right? If I put a negative 3 into my machine, the first thing that happens is it gets raised to the fourth power and it becomes 81. And the next step, 16 minus 81 becomes negative 65. I think that's right. Negative 65. And then that's okay. But then the next thing that happens is we try to take the square root of negative 65. And the square root of negative 65 is not a real number. So that's why there's no point on my graph where x is equal to negative 3. Negative 3 is not a part of my domain, because at that step we've broken the machine. The square root fails. Let's assume for the moment, though, that the square root succeeds. What about this last step? This last step involves a reciprocal. And it's that 1 over blank part that also introduces a new restriction. And that restriction is that we cannot take the reciprocal of the number 0. Right? If at this last step we've made it all the way through the machine to here, and this quantity is 0, in fact, that's exactly what we saw happen when we used x equals negative 2 in my machine. Right? By the time my machine got to here, this number was 0, and then the machine broke trying to take the reciprocal of 0. So we have sort of two things here that are fussy, two things that we need to be able to rule out them breaking the machine. So if we're going to do an algebraic solution to this problem, we're going to take these two pieces, the square root piece, which is going to require that x be greater than or equal to 0, and then also the reciprocal piece, which is going to require that the quantity be not equal to 0. And to figure this out algebraically, we'll take this and say, what is it that I'm taking the square root of at that stage? Whatever I'm taking the square root of, I need that thing to be greater than or equal to 0. And at that stage in my evaluation of the function, what's underneath my square root is 16 minus x to the fourth. And so, if I want to know how to satisfy my square root, I need to solve the inequality 16 minus x to the fourth is greater than or equal to 0. When I solve that inequality, I find out by adding x to the fourth to both sides that x to the fourth needs to be less than or equal to 16. And when I take the fourth root of both sides, I get the absolute value of x on the right side, and I get 2, the fourth root of 16, on the other side. And now I have one of these absolute value inequalities. I'm going to reverse it so that it's a little easier to read. Absolute value of x less than or equal to 2. Well, when it's a less than or equal to that I have my absolute value bounded from above, that means that when the absolute value disappears, we end up bounding that quantity on the left and the right side. And we find out that x, in order to satisfy this square root step of the inequality, x needs to be between negative 2 and positive 2. Inclusive, in this example, of both negative 2 and positive 2. That's what's going to make my square root happy. Minus 2 less than or equal to x less than or equal to 2 must hold, in order that my square root not break. But then once the square root is done, the last thing that happens here is we're ending up taking a reciprocal. And because we're taking a reciprocal, 1 over something, then whatever this something is down here, that something cannot be permitted to equal 0, because we cannot compute the reciprocal of 0. Well, what are we taking the reciprocal of? We're taking the reciprocal of the square root of 16 minus x to the fourth. And so, in order that that last step not break, we need to ensure that x satisfies the inequality 16 minus x to the fourth is not equal to 0. To solve that inequality, let's square both sides to get rid of that radical. 16 minus x to the fourth is not equal to 0. We'll add x to the fourth to the other side. We'll get 16 is not equal to x to the fourth. And then when I take the fourth root, I get the absolute value of x cannot be permitted to equal 2. And then removing the absolute value, x cannot equal plus or minus 2. And so in order that that last step not break down, the last step in my machine, I also need it to be the case that x is not equal to 2 and that x is not equal to negative 2. So x not equal to negative 2 and x equals not equal to positive 2 must hold. And in order for my machine to work from end to end, we need both of these statements to be true. We need x to be between negative 2 and positive 2, but we also need x to not equal negative 2 and positive 2. And so we find out when we take the intersection of those two inequalities that x must be between negative 2 and positive 2, exclusive of both, and that's where my domain interval, -2 to 2, exclusive of both endpoints, comes from. So finding the domain using algebra is mostly a process of just asking yourself what could possibly go wrong, and then following the consequences through to their logical endpoint. I'm just going to take about a break of 10 or 15 seconds in the video here, just to wet my whistle a little bit, get my voice back. And then we're going to talk about symmetries and transformations of graphs to close out today's live stream. most important skill is to be able to look at an equation like this one, y equals -3 radical minus x plus 5. So that's the graph of a function. And the two things that you'll need to be able to do is, first of all, list the individual transformational steps that can turn the basic shape of this graph into the shape that the transformed graph ultimately has. And then once you have those steps listed, also be able to sketch a reasonable representation of the graph of this function. So particularly in examples where there's more than one step involved in the transformation, it's not always obvious right away how to go about this process. So that's why I wanted to have this conversation now. So it's a three-step process. The first is identifying the basic shape of what this graph will look like. The second, which takes the most time, is listing out one by one the individual steps that will transform the basic graph into the graph we want. And then the third step, the graph. So the first step is usually the most straightforward. When you look at this equation, what basic shape of the graph do you see? Or what equation might define the basic shape that this graph will take? Right? Yeah. So the basic shape of this graph is going to be the shape of the graph y equals the square root of x. And what is the shape of the graph y equals the square root of x? What does it look like? It's half of a parabola, kind of sideways. So there's the basic shape that our graph is going to be built upon. Now from here, I always like to compare this to one of those silly word puzzles where you start with a word like fish and you end up with a word like hook or something. And you're supposed to turn the word fish into the word hook by changing one letter at a time as you go along the way. And it's supposed to still be a word every time or something like that. Okay, so maybe I'll change this to, well, that's not really a word. You know what I mean. You've seen these puzzles before. Husk. Hook, right? That's the idea behind what I'm thinking of, the way I think of listing these individual transformational steps that get us from the basic shape to the final shape that we're looking for, by changing one letter. In other words, I'm making one transformation at a time. So when you look at this equation, this formula, what kinds of transformations do you see between reflections, stretches, shifts? What's going on in there?
Stretch, reflection, and shift.
Okay, so you're seeing one of each. Does anyone not agree? What you got?
See, two reflections and shift.
Okay, so you're seeing a reflection here. Where else do you see a reflection? In front of the 3? Okay, so there's a reflection, there's a reflection. Where's the shift? Plus 5 looks like a shift at the end. What's this 3 doing? It's a stretch, right? So I chose this example because it has a little bit of everything going on. It's got some reflection going on because, well, how do you recognize a reflection when you see it? A negative sign where? Right, exactly. So either we place the negative sign in front of the x, we multiply the x by -1, or we put a negative sign in front of the whole expression, which multiplies the y by -1, essentially. Right? So we're doing some multiplication by negative numbers. That's the calling card of a reflection. We're also seeing a stretch. And how do we know that this 3 is a stretch? Multiplication, exactly. We'll talk about what kind of stretch it is in a moment. And then how do we see a shift? What's important about looking for a shift? Plus 5. And why is plus 5 a shift and not a stretch? What's important about it? It's outside of the square root. So first of all, it's something that's happening to the entire expression on the right-hand side. That's how we're going to know that it's actually a vertical shift. But how do we know that it's a shift in contrast to a stretch or a squish?
It's being added.
It's added, right? Addition and subtraction are the calling cards of shifts. Multiplication and division, stretches, squishes, reflections, but never shifts. Shifts are always adding and subtracting. So we have a little bit of everything. And so it's a completely necessary, I would say, question to ask yourself in this example, if we have all three of these things going on, which should we worry about first? And here's the problem. Here's why this is an important question. Let's suppose that I were to first worry about shifts and then worry about reflection second. So we've got a shift, we've got a reflection. Let's suppose we shift first and reflect second. Take a look at what would happen. Our shift is plus 5 here at the end. So which direction does that shift move our graph? It's moving it up. Again, because it was done to the entire expression, something vertical is going to happen. It's operating on the y. And when you operate on the entire expression, things happen not in reverse, but in the way that you expect them to. Adding 5 moves the graph north, moves it up by 5. And so 1, 2, 3, 4, 5. So here's what that transformed graph would look like. And what would the equation of this graph be after we just apply that one step of shifting up by 5? Square root of x. And then plus 5, and where does the plus 5 go? Because we operate on the whole expression, plus 5 goes on the outside. So that's going to be the shape of the graph that we see over there on the right. So if we decided to do the shift first, then that's where we would be. All right, but now suppose that we want to do a reflection. Let's say I want to reflect the way the book says it. Let's say I want to reflect it over the x-axis, or about the x-axis. In other words, this would be a reflection which flips our graph from top to bottom, right? What we used to call a vertical reflection when we talked about this before. If I do that to this graph, then this point right here, which used to be at 0, 5, if I flip that over the x-axis, that point is now going to be at 0, -5. And my graph, which used to be increasing as we go from left to right, if we flip it over the axis, our new graph is going to be decreasing as we go from left to right. So this green curve down here on the bottom would be the result of reflecting the blue curve across the x-axis. I suppose I should have labeled my axes. Let me add those in here. X-axis, y-axis. All right, now here's the tricky part. What would the equation of the green curve be? Algebraically, what are we doing if we're reflecting something over the x-axis? Yeah. Multiply everything. How do we know we're multiplying everything by -1? And not just, say, multiplying the x. Yeah, that's what we're doing functionally here. So we're just going to put a minus in front of the entire right-hand side here. So I have square root of x plus 5. But I'm interested to know, why did you decide to multiply everything by -1 instead of, say, putting minus underneath the square root? What is it about our step here that tells us we want to multiply everything and not just multiply the x? Yeah.
Because you want to make the whole line decrease, not just go back to line.
Okay. And what kind of a reflection is that? I mean, are we changing, which coordinates are we changing? Are we changing x coordinates or are we changing y coordinates? Changing y coordinates. So since we're changing y coordinates, we want something vertical to happen. When you want something vertical to happen, you have to operate on the y, or another way to do that is operate on the entirety of the expression. Right? So we wanted a vertical change, so we operate on the entire expression. We put a minus sign in front of it, and then we get y equals minus the quantity square root of x plus 5. Can we simplify this to get rid of those parentheses? What would that look like? Yeah. Oh, that's we got the yeah, change which signs? Yeah, exactly. In order to get rid of those parentheses, we would have to distribute the minus sign. And there then would be an equation for this final graph down here, y equals, the minus the square root of x minus 5. Okay, but now I want to pause for a second and ask, are we getting closer to the equation that we're looking for, or did we go wrong somewhere? Yeah, so how do I know that maybe I'm in a little trouble now? What do we want that we don't have anymore? Yeah. Yeah, exactly. The big difference here is that we started out adding 5, and we did that because we knew we wanted a plus 5 in our equation ultimately. So we had it. But then after we reflected, we lost it. We used to have a plus 5, now we don't have it anymore. So this is why order is really important when you're listing multiple steps along the line. Because if we shift first and then reflect, we might get a different result than if we were to reflect first and then shift. So we could end up getting something that we wanted and then losing it later on down the line if we're not careful. So here's my recommendation for how to avoid falling into this trap, which is such an enticing trap to fall into. Here's how you can avoid falling into this trap. Always save all of your shifts until last. Shifting should be the last thing you do. Another way to think of it might be follow the order of operations. Order of operations tells you multiplication and division always happen first. Addition and subtraction happen last. It's the same thing with transformations of an equation to avoid falling into the kind of trap that we just fell into. Save your shifts, your additions and your subtractions for last. And take care of all of your reflections and your stretches and your squishes first. So I agree with what Emily was saying. We want to reflect, then shift. Not shift, then reflect. So let's try that instead. If I start by reflecting vertically, what's my equation going to turn into? Y equals. How do you reflect the graph vertically again?
Negative square root of x plus 5.
Right, and I don't have a plus 5 at this point. I'm just starting over, basically. So if we just reflect vertically, we just have to multiply the right-hand side by -1, and that accomplishes it. So y equals minus the square root of x. That's going to take us to here. And now we've got that reflection done. We still don't want to shift yet, because we still have more stuff to do. What else can I do before I do any shifting? What other steps should I think about? What else do you see in this equation? Stretch. What kind of stretch? Or what part of this formula is telling us about stretch? Okay, so that multiplication by 3 is a kind of stretch. What kind of stretch? Is it vertical or is it horizontal? Is it happening to the whole expression or is it just happening to the x? Vertical, because? How can you tell? Right, it's being applied to the whole function. I'm taking this whole expression minus the square root of x and I'm multiplying it by 3. So I'm really operating on the y, which is a vertical change. So I'm going to take this graph and I'm going to stretch it out vertically so it's kind of 3 times as tall as it used to be. Y equals minus 3 times the square root of x. We'll then have that shape. All right, so now we've taken care of a reflection, we've taken care of a stretch. Are we done? Can we start shifting, or do we want to do one more thing? Talk about a leading question. What else must I do before I do any shifting? Mike? Yeah, and how can you tell? What's telling you that we need to do that? Yeah, yep. So we replace x by minus x, because underneath that radical is a negative sign, or a minus sign, I should say. So replacing x by minus x does have the effect of flipping that graph horizontally. So this now is y equals minus 3 times radical minus x. So we've done 3 steps now, starting from our original basic shape. We reflected it vertically to introduce the minus sign outside the radical. We stretched it by a factor of 3 vertically. That introduces a 3 outside the radical. Then we reflected horizontally to introduce the negative sign under the radical. And now we've taken care of everything in this expression with one exception. We can finally do our shift. Because everything else is taken care of. Oops. And the last thing we need. Uh-oh. Make a mess out of this here. And the last thing we need, and that we're now ready to do, is that shift. And as we observed before, that's a vertical shift, up by 5. So y equals minus 3 radical minus x plus 5. And we've arrived at the equation that we were looking for. And all I have to do to get the graph is take this green curve and just bump it up by 5 units. And then we'll be done. So 1, 2, 3, 4, 5 is right there. And so I'll just kind of sketch that in. And that completes the problem. So our final answer then is this graph. Y equals minus 3 radical minus x plus 5. That's where we're going to wrap up for today. Sorry, I had muted my mic. So we covered a lot of ground, but sort of got an introduction to what the idea of a function is and how some properties of its graph relate to some properties of its formula that defines it. This really is a week where we've set the stage for the rest of the course, because everything that we study from here on out in pre-calculus is going to be studying a function. And we'll study it from those 4 different vantage points, right? From the algebraic perspective, from the graphical and the numerical data table perspective, from a verbal perspective. But really, this is what the business of mathematical analysis, so pre-calculus, calculus, differential equations, they're about the study of functions and their properties. And so that's going to be a theme, and everything that we do from here on out is going to relate to the foundation that we laid in today's live stream. So sorry it went a little longer than usual, but I hope you find some usefulness in today's video, and I look forward to taking those next steps.